everyone. Thank you for joining me today. My name is Janice, and I am a first-year master's student working in the Heinz Lab. I am very excited to share with you my project, which focuses on training salmonella through conditioning using a megaplate approach. When we hear the words training and conditioning, many of us will remember the famous Pavlovian dog conditioning experiment. This is where Pavlov repeatedly paired the sound of a bell with food. Eventually, with enough repetition, the dog learned to associate these stimuli and would salivate at the sound of the bell alone in anticipation of food. So what might this look like in bacteria? Well, instead of a bell, the first stimulus might be a nutrient or chemical, something the bacterium can sense. Most importantly, this stimulus must be neutral, meaning it does not inherently elicit a response related to the subsequent stimulus it gets paired with. For a second stimulus instead of food, it might be a stressor. In theory, if the neutral stimulus is always present just before the stressor, the bacterium may be able to form an association between these stimuli and learn to anticipate the stressor and elicit the stress response after only encountering the neutral stimulus. Since bacteria live in dynamic environments, anticipation is very useful. When changes are predictable, bacteria that can forecast or anticipate these environmental shifts and mount an earlier response to an upcoming stressor are often more fit. In bacteria, instead of Pavlovian conditioning, we call this adaptive prediction. One of the few groups that have been able to successfully train new behavior did so by repeatedly pairing caffeine with an acid that yeast can then metabolize into a toxin. Survival assays revealed that yeast that were conditioned with caffeine prior to acid exposure had increased survival relative to yeast without conditioning. This is a promising study demonstrating how novel environment structures can lead to new behaviors through adaptive prediction and coupling of response pathways that were previously unrelated. However, literature studying the ability of bacteria to learn new behaviors is quite limited. That brings me to my research question. Can we quickly reshape our bacterium of choice, Salmonella typhimurium, to introduce new conditioned responses by pairing a stimulus of low evolutionary cost with a stressor? Studying conditioning, whether it's possible or not, and the factors involved, will help us further understand how bacteria have come to evolve. We're interested in Salmonella because it has a well-defined natural history through the gastrointestinal tract and displays several instances of anticipatory behavior. This suggests that its genome likely already has seemingly unrelated co-regulatory networks, which can be a starting point for selecting stimuli and stressors. For example, Salmonella typically only encounters iron in the gut lumen. However, it responds to the presence of iron not by upregulating genes needed in the lumen, but rather the iron-deplete epithelium, the subsequent environment. Here we have two unrelated stimuli that are paired, resulting in anticipatory behavior. Our approach involves using the megaplate, which stands for Microbial Evolution and Growth Arena. This is a 2x4 gate plate with built-in partitions to create a physical landscape consisting of different media conditions. Motile bacteria are inoculated at one end of the plate and then allowed to swim across. The megaplate is a powerful method of investigation for several reasons. First, this design makes it relatively easy to separate the winners and losers. Winners are bacteria that have acquired anticipation and spread across the plate faster. Losers are bacteria that have not acquired anticipation and are left behind. Secondly, time series imaging allows us to track variant lineages and follow evolution real time. By sampling and analyzing variants of interest, we can reconstruct the evolution that's occurred. Also, the large size of the plate lets us simultaneously challenge large populations of bacteria to increase mutational supply. For our megaplate, the first layer of agar will determine the physical landscape, which consists of multiple repetitions of the regular agar, neutral stimulus, and stressor. The arena can be organized such that the bacteria will always encounter the neutral stimulus just before encountering the stressor. The second agar layer overlays the entire plate and functions to level off the first layer. This will also prevent bacteria from interfering with the partition. The third layer consists of a swim agar overlaying the entire megaplate. Finally, bacteria are inoculated at one end of the plate with regular media and imaged. The megaplate we're building is a 2 by 4 feet dish with 9 built-in partitions to minimize diffusion between media conditions. While I'm currently working with Bert Bichot to build a full-size megaplate, I've been experimenting with a mini version, which I've shown here on the right. Here I show time series imaging of the mini megaplate that captures the evolution of streptomycin resistance. This plate has a forced lab concentration gradient of streptomycin with salmonella inoculated on the left side of the plate. Here we can see that the streptomycin sensitive strain shows evidence of stalling and acquisition of resistance. For my future directions, I will be selecting a stimulus stressor pairing to start my conditioning experiments. This pairing must satisfy 2 criteria. 1, the fitness advantage should be unidirectional, and 2, preparation should be costly enough such that when the stimuli are no longer paired, the association is lost. To conclude, from my preliminary work, the megaplate is a powerful tool for studying conditioning in salmonella and visualizing evolution as it happens in real time. Further investigation will allow us to better understand how bacteria evolve and how they exploit memory to problem solve. I would like to thank everyone in the Heinz Lab, my committee members, Dr. Surratt and Dr. Coombs, as well as my supervisor, Dr. Alex Heinz. I would also like to thank my house pets, Charlie and Yaxley, who was featured earlier in my presentation. I could not have done this without all their support. And thank you for listening.